Okay. Hi, everybody. Thanks for listening in. This presentation will focus on the properties of the planet Mars. Mars is, of course, a very interesting planet for a variety of reasons. Uh, in some sense, it's the most Earth-like of the terrestrial planets in terms of its surface conditions. It's also been explored quite heavily by various spacecraft. For example, this is the Curiosity rover, which is roughly the size of a small car, which has been making measurements on Mars for a few years now. What's nice about these rovers is they give us a human scale picture of Mars. Even though this thing is the size of a small car, this camera is about at human level. And so you can get pictures like this, which provide you a kind of sense that Mars is indeed somewhat Earth-like. This is a sunset from the Curiosity rover, and this could be a sunset on Earth for all you can tell. This is a landscape picture from the Perseverance rover, and this looks like various places in the American West. So this gives you an impression that Mars is quite Earth-like. Now, if you know your details, there is, of course, significant differences. And there are some important differences between Mars and Earth, both in terms of their global properties and this environment that these spacecraft are operating in. On the global scale, Mars is, of course, smaller, but it's also less dense and has a weaker magnetic field, which indicates very different aspects about its composition and just how it works as a planet. In addition, its environment is quite different. The atmosphere on Mars is extremely tenuous, less than 1% the atmosphere of Earth. Its temperatures are much lower, which means that liquid water can't exist on its surface today, which is completely unlike Earth. So we're going to discuss both these differences in global properties and its environment a little bit today. Okay, so let's first talk about these global properties. The most prominent of which is Mars is considerably lower density than the Earth. The Earth has a density of 5.5 grams per cubic centimeter, which is intermediate between the density of rock and metal. That's why we think Earth has a fairly large core, and Earth also has a strong magnetic field, which tells us that that core is liquid. Mars has a density of about 3.9 grams per cubic centimeter, which is not as low as the moon, but still significantly lower than Earth. That suggests that Mars's core, if it's there, is smaller. Also, Mars doesn't have a magnetic field like Earth. The reason for that is still unclear, but one option is that that might mean there's not a liquid layer there because Mars is smaller, it loses its internal heat more efficiently, so perhaps its interior is frozen or more frozen at least. But we really didn't know. And in fact, part of the goal of one of the missions to Mars, called the InSight mission, was to try and figure this out. And it was going to use multiple ways to do it, but the one that's produced some interesting results recently is from a seismometer. Remember, the reason we know so much about the Earth's interior is because of seismic data, by listening to earthquakes and figuring out how they propagate through the Earth. It would be great to do a similar thing on Mars. And this mission did bring a functional seismometer to Mars that's called the SEIS instrument. It's shown here in this picture from the lander that brought it there, that has been sitting on the surface listening for earthquakes for a couple of years now. Sorry, listening for Mars quakes over the last couple of years now. And it has detected them. Mars is not as geologically active as the Earth, so Mars quakes are rarer and weaker, but it has detected some. And the ones it has been able to measure have revealed some important things. In particular, there are echoes within those signals. So if InSight, the rover listening for this, or the instrument listening for this is a lander, not a rover, is right here, and the source of those emissions of those Marsquakes is over here in a series of fissures, the signal they hear has two components. One is coming directly from them along near the surface to the instrument. Another, which takes a longer time to get there, goes down, bounces off something, and gets back here. Now, this is observed on Earth as well. To get these sorts of reflections inside the planet, you need a layer. And one of the big layers in Earth's interior is the boundary between the liquid metal core and the more solid rocky mantle. This reflected signal has the same sorts of properties. So the implication is that this echo is coming from the boundary between Mars's liquid core and its more solid mantle. Now, the properties of this are consistent with Mars actually having a liquid core. So Mars has not lost enough heat for its core to freeze yet, which is interesting. There's also then the question of why is that liquid core not generating a magnetic field like Earth's does? We don't know yet. Another interesting result from this is it gives us the size of the core. Turns out that this signal gives you the location of that interface. And it was not quite where people expected. The core of Mars is still quite a bit smaller than the core of Earth, but it's bigger than was expected. The core radius here is a fair fraction of Mars's radius, and the density of the core that you get from that works out to be about 6 grams per cubic centimeter. Now remember, metals tend to have densities of around 8. So this is less dense than pure metal. And it's less dense than the metals we know exist in Earth's core. The suggestion is that whatever this metal is, it's mixed with something that is lower density. Things like sulfur and perhaps other elements like oxygen. This is different from Earth's core, and the implications of it are still unclear. Why is Mars's core less dense than Earth's? Is it just because Mars has less gravity and that's affected the composition? Or does it reflect something fundamentally different about how these planets formed and the way the metal separated from the rock on these two planets? This is something that people have just found this summer, so this is something still to be understood. Now, so that's one way that Mars is different from Earth. If we start looking at the surface and the expression of geologic activity on Mars, we see other differences that are worth keeping in mind. Mars seems to excel in having very big things, not just big craters. It does have a few of those, but it also has examples of geologic activity which are large, even compared to features here on Earth. For example, there's this gigantic valley called Valles Marineris, which is a large tectonic feature even by Earth standards. It extends across a fair fraction of the planet. Mars also has very large volcanoes. There are 4 in particular, Olympus Mons and these other 3, that are found all in one place, and these are larger than any volcano seen on Earth, Olympus Mons is specifically. So now these features are fairly old, consistent with the fact Mars is smaller and thus geologic activity has probably toned down a bit, You can see there's a few craters on the surfaces, but it's surprising that they're so big. Now, there's a couple of reasons for that. One reason is Mars is smaller. Being smaller means that Mars doesn't have the same gravity as Earth. Just like on the moon, how the astronauts could jump around a lot because the gravity on the moon is smaller than the gravity on Earth. The gravity on Mars is not that extreme, but it is less than the gravity on Earth. That means that it's easier to pile stuff up because you have less weight pushing things down to try and flatten things out. So this helps in creating very tall, big structures, but that's not the whole story. There's another aspect to it, which is that the geologic activity on Mars seems to work in a fundamentally different way than the geologic activity on Earth. And this has to do with something called plate tectonics, which is important for Earth, but not seems to be operating on Mars. Now, what do I mean by that? Well, on Earth, geologic activity is not uniformly distributed. This is a map showing the locations of major volcanoes on Earth. And what you see here is the famous ring of fire around the Pacific Ocean. This edge has way more volcanoes, active and extinct, than other parts of the world. Hopefully you all know this. Washington has volcanoes. California has earthquakes. Neither one of those exists in Kansas very often. And that's not just in the United States, that's all over the world. You can see that volcanoes tend to organize into lines. The reason for this is because of how volcanic and tectonic activity works on Earth. The idea is Earth's surface is divided into plates. Basically, there are nearly solid plates of material, and what we're seeing here is where two of those plates are either being pulled apart or crashing into one another. So you have basically all these motions happening deep interior, which can create like new surfaces, like in the center of the Atlantic Ocean, which can push these solid plates on top of other plates, like the one of the Pacific Ocean, causing those plates to fall, to get pulled down, then melt, and then you produce material that erupts, or produce hot spots, which erupt in various places. But the basic evidence we have on Earth is that these plates are constantly drifting around on top of something, on top of the hotter, easier to move material of the mantle. And the thing is, this has implications for how geologic activity, and particularly volcanoes on Earth, work. It means that if one of the ways you can have geologic activity is at one of these interfaces, but because the plates are constantly moving and eroding and crashing into each other, they're not going to happen at the same place at all times. The other way it happens is you can have a place where there is some material in the mantle that wants to go up, producing a hotspot that wants to create a volcano. But because these plates are moving, that material erupts at different locations erupts at different points in the crust at different times. The classic example of that is Hawaii. Hawaii is a major volcano on the Big Island of Hawaii that corresponds to a deep hotspot that is causing rock to melt and move towards the surface. But since the Pacific plate is being pushed around, the position, that location where the material is erupting is constantly changing in the crust. So although the eruption is happening at this location in the crust now and making the big island of Hawaii, it occurred at other locations further in the past, corresponding to these different islands. So this eruption is happening, and as the crust drags over the surface, you get an island built up, but then the source of that island gets removed, and the island erodes due to erosion, due to rain and other things. So you don't build up one single volcano, you get a whole bunch of them. This is actually happening in Idaho too. Yellowstone is a center of potential volcanic activity. It's where heat is escaping from the interior of Earth in the middle of the North American plate. It is that hotspot currently sits under Wyoming. But in the past, as the plate has shifted, that's a recent development. In the past, that hotspot was in Idaho and contributed to various things like the craters of the moon. On Mars, this doesn't seem to happen. We don't see that the volcanoes are arranged in nice lines indicating plate tectonics. Instead, the volcanoes are localized in groups. This is a big map of Mars with different terrains marked. And the volcanic features are mostly concentrated in two regions. The big volcanoes are in this region called Tharsis, and there's another group in a region called Elysium. There's no indication of a linear trend per se, which indicates that plate tectonics isn't happening. So the surface and the material on the surface isn't slipping relative to hotspots. So if there's a place where stuff is erupting, it just keeps erupting in the same place and builds up big volcanoes instead of the surface drifting relative to this stuff and building up a lot of smaller volcanoes. That at least seems to be the case. And it's part of the reason why Mars seems to have such large structures. Okay, so that's some interesting points about Mars's geology. We also should talk about Mars' environment, which is quite different from Earth today. Mars' environment is currently very different from Earth's. Its atmosphere is almost entirely carbon dioxide, and it's less than 1% the atmosphere of Earth. That is, the total amount of stuff in Mars's atmosphere is 1/20th the total amount of stuff in Earth's atmosphere. So it's very tenuous. That together makes the surface of Mars very cold. It's like 210 Kelvin or about minus 80 degrees Fahrenheit. So it's cold, but not unimaginably cold. It is cold enough that liquid water can't exist anywhere on the surface of Mars, which goes along with all the pictures. You either see regions like this, which are superficially Earth-like, but clearly something more like a desert than anything else, or it's frozen solid. There are ice caps of water ice and carbon dioxide ice at the poles. So at the current moment, Mars's environment is very unpleasant for Earth-based life. But what's interesting is that there is also evidence that it hasn't always been that way. If we look at satellite pictures of Mars, we start to see features like this. There are obviously craters, which are, again, mostly impact features indicating the surface is old. But in addition, you see these valleys, which look very much like erosion. and not erosion due to wind. This looks like a river valley. This is erosion due to a liquid, and the most likely one is water. Now, there are a variety of these kind of structures. Some of them look like this. They don't have many tributaries, and the tributaries they have are stubby. These are typical of what might be created by groundwater sapping. Other ones look like this. They have many thin tendrils. These are what more you would see due to atmospheric water. Like this is what literally, regions where you have a lot of rain, the rain flows down, creates small tributaries, which merge together to become larger and larger rivers. This looks like water from the atmosphere. This looks like water from the ground. So there's implications that there were times when Mars had liquid water near or above, near its surface or in its atmosphere. Now, the thing you might notice about these features, like this one, is there are craters on them, indicating they are old. Now, some of these features are quite big, just to say it. This is a picture, zoom in on this part of Mars. This is a topographic map of Mars. So blue colors are high altitude. Sorry, red colors are high altitude, blue colors are low altitude. This is a gigantic impact crater. This is a gigantic impact crater. If we look here, we can see there is a gigantic, what is called outflow channel of material flowing from high altitude to low altitude. This indicates a fair amount of water was flowing at some time in the past. Now, beyond this, now again though, if you look closely, you will see there are some impacts into this stuff, indicating that it's ancient. Now, on the other side of the side scale, apologies, the rovers have shown things that look a lot like rocks created in water-rich environments, that it's bedded, it's sedimentary rock. There is also rock that is clearly volcanic, but there's evidence for sediments. And these are rocks that are of high interest because sedimentary rock implies erosion, implies liquid water, it implies all sorts of things that are interesting from both a geological and habitability perspective. Because if you have liquid water running around long enough to make deposits like this, maybe something was living there. This is actually what the Curiosity and Perseverance rovers are looking at right now. Curiosity was sent to actually investigate these types of rocks in detail. It carries a variety of instruments on board to make detailed measurements of them. So, but here's the thing. They are all ancient. All of the things that seem to indicate water was flowing are found in these elevated areas flowing into the other areas. These are regions with lots and lots of impact craters. You can see all of the circular features. There is a region up here, which is for some reason lower, we're still not entirely sure why, that has very few craters and also has very little evidence of liquid water flowing. The rovers, Curiosity and Perseverance, are on the boundary so that they can actually, it turns out it's easier to land at lower altitude. So the idea here is they can explore some of these features where they get out onto regions you can explore. So those flows are found all over the place. Also, these rocks that appear to have been processed by water, which come in a variety of forms. They are even analogous to clays on Earth. are also found in this southern, primarily in the southern hemisphere, in these regions of that are very old. And for very good reasons, that's where the rovers have gone, because that's interesting. But it does suggest that in the past, Mars was wetter than it is today. Now, getting actual ages for this is a little tricky. You need to use the moon dates to get a sense of impact fluxes and translate those to Mars. There's also the few Martian meteorites that help with that. But the idea is that before about 3.5 billion years ago, maybe, then Mars had quite a bit of liquid water on its surface. But over the course of time, turns out that it became progressively drier, probably as the water progressively froze and some was lost to space. And there are debates about when exactly this happened, but by about 2 billion years ago, Mars has started to turn into its current dry, cold, present configuration. Now, but the fact that there was this time when there were clearly liquid water on Mars has elicited a lot of interest because, again, this is a different planet. Did this process work like it does on Earth? And of course, there's all the interest in potential for life in those sorts of situations. So the Perseverance rover is taking the next step in this analysis. The Perseverance rover landed in this thing. This is in Jezero crater. It is a gigantic, basically river delta. There is a flow of material from here that comes through, and then that material spread out and deposited clays and other materials. It is, again, an old thing. You can see there's a couple craters into it. But the idea is that the rover is driving around on this thing and might drive out onto this thing later. And unlike the previous rover, which is studying them in situ, it's basically got its own instruments to measure it, to measure things about their chemistry and mineralogy, etc. This rover is collecting samples with the hope that it will be able to leave a set of samples somewhere so that another spacecraft can come down, pick up those samples, and bring them back to Earth, so that Earth labs can do detailed measurements of the chemistry, the structure, etc. of these rocks. We'll see how well that works. Just to say, though, there is intriguing hints that water on Mars may not be completely gone. Even though the water is mostly frozen, there's a good hint that water is kind of all over on Mars. It's just not on the surface. There are various instruments that can probe beneath the surface and measure basically hydrogen, which most often is found in water on terrestrial planets. And there's hints of water under large fractions of Mars. Now, this probably is mostly in the form of ice because it's still fairly cold. But it potentially can also be in the form of groundwater, in which case, if you could dig down, you could get to an aquifer, which would be interesting. And there's a few features on Mars that indicate that such things could exist. This is a picture of a region of Mars which has a fairly steep slope. This is the background material. This is basically probably a crater. And it's got this steep wall. And what you will see here are these streams that seem to come down from a particular layer in whatever is coating the surface. And These things are called gullies or recurrent slope lineae because what's interesting about them is they change over time. These are two pictures of a couple of those things, one from 2011, another from 2013. And if you look, for example, at this one, you will see as you go for over 2 years, it gets longer. So over the course of a couple of years, this changes. That implies there's something happening right now that's making these things. These are not ancient structures, they're recent. And one possible thing that could be happening is this sharp edge is cutting through a layer of either ice or water. And over the course of seasons, that water sometimes leaks out of that layer and comes downstream, forming these extra little trails. Now, a big debate, which I will say I'm not an expert in, is whether these are water flows or just tiny little landslides. But these are one of the most promising locations to look for water today. Accessing these, because they involve steep slopes, is really, really hard. And so people are still debating how to do that properly. But this illustrates just where people are interested in figuring out the climate history, the potential of life, and the structure of Mars itself. Thank you for your time and attention.